we will solve a problem which is related to the concepts of equilibrium and all the tools, techniques, methods which are required to solve such a problem. We have already seen in the theory sections, and in solving these problems we will solve many problems, and these problem solving actually will tell you how those techniques will be actually used in practice. Okay. So now, and then if you see them, problems will generally be given in pictures, okay, and because they are engineering problems, and you have to first thoroughly understand the configuration. That's the major part of the solution process. In fact, that I would consider that would be the most important part of solving any problem, engineering problem. From the drawing you should be able to understand what this structure means. Okay. And then the job is to draw the free body diagram, because we have discussed that whenever multiple bodies are connected, this is the multiple body connected problem, and where the main idea is to break them down into different segments or different objects connected through different types of connectors. Okay, so that is what is the first step to do, and then comes the equation writing and then solving, and we will see each of those things step by step, and then I'll be pointing out where we are using what skill that we have developed through our theory portion. Okay, now coming to this problem. The question what it is asking is, this is a structure which is shown like that, and this pulley has got a, in fact, mass also of 200 kg. Okay, and then all other bars are massless, means you can assume them to be massless. So that's what has been mentioned in the problem, and then you are supposed to find out the reaction force between these two members. Let me first tell you, in fact some of the students face even problem in understanding this configuration. Let me first tell you what it means. Okay, so there are in fact for me there are 4 bodies in this except ground. If you include ground, then there are 5 bodies, and what they are, say first thing is a BD. BD is a straight rod like that. Okay, this is B, this is D, and this rod has got say 3 points here where 3 other things have been joined. Okay, for example, this side is connected to the ground, this point is connected to the other rod, and then this point carries a pulley, a frictionless pulley. Okay, and similarly the second object, which I would say is something like this. Okay, here this has got 2 joining points at which this body will be joined to the full structure, are these 2 points, and yeah, so this point is the point where it is connected to the other rod, and this is the point at which the thread or the rope is connected, and then there is another body called the pulley. Okay, which is having a mass of 200 kg, and then there is a mass hanging from the thread which is of 5000 kg. Okay, now these are the 4 bodies, and then if you want, I will draw even the ground. Okay, so ground is like this. I'll write it ground. Yeah, ground. So there are 2 in fact hinge points like that. That's it. So these are 5 different objects which make our configuration or the structure, and then it is asking you to find out that say this body is AC, isn't it? AC. Now AC must be applying some force on BD, and BD must be applying some equal and opposite force on AC, and that force of reaction is the thing which is being asked in the question. And one more point here, here you observe that there is a uniformly distributed load. Remember we had discussed about continuous forces. So, and then whenever we apply a continuous force, it has to be written in terms of densities, force density. So Newton per meter has been mentioned, and this is applied for 2 meters. Okay. So this is the hinge point, and from the hinge point the distance is say 0.3 meters. So this is 0.3 meters from here, and then there is a 2 meter length of uniformly distributed loading, and then this is 4 meter, this is 2.5 meter, this height is 2.5 meter, and the radius of the pulley is 0.6 meters. So that's the dimensions of the complete structure. Okay. Then what you have to do is you have to show the free body diagrams. Okay. Now these are just the bodies, not the free body diagrams, because they should also show the forces which, when you remove this, for example this body, when you removed it from the structure, the connectors, they were applying some force before you removed them. So those forces must be shown on that diagram, and then it will become a free body diagram. Then let's show those forces. So at B, what sort of forces will come, because it's a hinge point or a pin joint. So you will have to show the x direction and y direction forces. Before that, let me draw a coordinate system, say like that. So we are saying this is x direction and this is y direction, and it's a 2D problem, nothing is in the 3D. So you can consider this as a 2D problem. So okay, now we can always say that there is a reaction here, say Bx and By. Okay, Bx, By are the reaction forces, and the idea or the trick which you can use in drawing these forces is you ask this body, okay, ask this body whether if I move you down in the y direction, will the ground react? If the answer is yes, then you put this force By, and in the sense doesn't matter, you could have put actually in the downward also upward. After calculation, the actual sense we will get. If it is negative, the number negative is coming up, then we will say that okay, our initial assumption was wrong. Okay, and then you ask again the body that if I move you in the x direction, if I pull you in this side or that side, if I push you on this side, will the ground react? The answer is yes. Then you put this. So this question is always very helpful in putting the reactions from a connector. And now coming to point C. So this is the point C, right? Now again you ask the body that if I move you down, will the pin joint at C react? The answer is yes. So you can put maybe this force, say Cy, and similarly from the same question in the x direction you will put say Cx. Okay, and then you should ask also about a rotation. In fact, you could have asked here also that if I try to rotate you, you are asking the body, if I try to rotate you about this point, will it react? The answer is no, because it's a free, completely frictionless pin joint. Similarly, if you ask that, okay, if I rotate you about this point C, will the pin joint react? The answer is no. So you won't put any moment over here. Okay. And then similarly, if you ask at D, you will again see that say dy and dx are the forces which you should show. So this is a proper free body diagram of that particular body. And now coming to similar up to, at this point, so again the same thing. At A you should have AX and AY, okay, and then what? At C, see, you have assumed that the body AC has pulled or has been or was pulling this body in this direction. That means when you show the force on this, exactly the opposite force should be shown. Okay, so that you have to be very careful about. Being consistent about the directions and senses of all the forces that you show. C, this is Cx, and in this direction, if AC was pushing this, then BD also will push this downward. So this will be, Cy. And is that all? No. So there is one more force that is coming from that string, right? So that point is actually in this direction. Say suppose the tension T, right? Now, so that is about the bar AC. In fact, here I want to point out one more thing. This shape doesn't matter. This could be any other shape which is rigid. Then also the problem doesn't change. The main important points are these 2 points. In fact, you should always also ask yourself to tell whether it's a 2-force member or a 3-force member. So these are, you see, at 3 points they are connected. So they are not 2-force members anymore. Yep. This also at this and this, there are 3 points on which it is the forces are acting. And now suppose I go here. So one is a suppose this is a force like that, this is a force like that. Say I'll call this as T, and this I'll call say T prime. In fact, we know that they must be same, obviously, because there is no friction inside the pulley. But just for the sake of it, I'm just writing it just to show that from the scratch that, okay, so how you should write your free body diagrams. Okay, so this is T prime. So that's how. So here again, so this body, this 5000 kg body was pulling this one from this side, so this also will pull from that. Achha, on this we have missed out something, right? So these dx dy's must also be shown. For example, at this dx, pulley was pulling it, so pulley the BD will also pull in this direction. So if this is dx and this is dy. Okay, and one more force, that because of that 200 kg, so a force will come, in this direction as well, say mg, m being 200 kg. Fine. So then what? If that is the case, free body diagram of the pulley, and this is it. So in fact, here you could have shown, it doesn't matter because the ground reactions, they will just come exactly the opposite like this. So for completeness, I am doing that. Vy, and here it's Ax and Ay. Nothing else. Yeah. So these are all the free body diagrams which you would require to solve the problem. or to find out, because here when we say solve the problem, that means we are intending to solve for these two numbers. Okay, one important point to be observed here is in this problem there are many forces which actually we cannot completely solve for. Okay, if you count the number of unknowns and the maximum number of equations which we can write, you will see that we won't be able to solve all the unknowns. But because the question is asking us to find some specific forces, we will try to figure them out, so that would be possible. Okay. So then what? So let's see. There are some simple calculations which can be very easily done. So let's do them. So when we consider the equilibrium of this body, okay, that means T prime, I'll call this as a capital Mg. So T prime say, so now T prime obviously will be this capital Mg, right? Because this is in balance, so T prime minus that will be 0. So this is the first thing, where M is equal to 5000 kg. Okay. Then if T prime is that, so its job is done. So no more information we can extract from this free body diagram. So let me call this FBD 1. Say this is FBD 2. Sorry. Say this is FBD 3. And this is FBD 4. 4. And this is 5. Okay. Now let's say, so this is done. FBD4 has done its job. Then what about say FBD3? Because this is one more simple thing. From where if you take the moment about this point D, right? So this is D. So if you take the moment about point D, why we are taking moment about D? Because there are many unknowns which are going through that. So dx dy we don't know. So if you take moment about that, you can just get rid of those unknowns and you have equations only with these two. Okay, see, you could have simply written that t equal to t prime, because you know that when there are no frictions, so that's the thing which happens. But I am just trying to show that how the free body diagram is used to write that. Okay, now if you sum all the moment about that point D, and that should go to 0, so that means t times this r. Okay, so t times r. So here I am writing the scalar equation of the moment. I am not writing, because it's a very simple case, so I am not getting into the r cross f. I am simply writing the scalar version. So t times r is equal to t prime times r, which gives us that t is equal to t prime, which is also equal to that 5000 times g, so mg. So this is nothing but mg. Okay, so that is one. And then here you can actually write now the force balance. So say let me write these things as, say this is step 1, say this is step 2, say this is step 3, is if I write the summation of the force in x direction, okay, here in FBD 3, then what are you getting? Equal to 0. So from there you simply can say that dx is nothing but t, because here if you write say dx, this is minus I, it is in the minus x direction, so minus t what I, this is also minus in this direction, okay. Then this goes to 0, implies dx is equal to minus of t, okay. So that means you are getting, is it fine? Okay, yeah. You will get a force of 5000. See, t is in this direction, so that means so this is coming to be minus mg, right? Okay. Acha, one more thing. I think I have not noticed that here it is mentioned Newton. Okay. So this is T prime is simply 5000 Newton. So okay, mg is 5000. So this is equal to 5000 Newton. It's not 5000 kg, but the whole thing is 5000 Newton. So that means actually it is 500, about 500 Newton kg. Yeah. Okay. So that was a wrong thing. So here it is 5000 Newton. Anyways, so this is nothing but negative of 5000 Newton. So see this negative sign here, which is coming, which tells you that the assumption that we had taken that this pulley will be pulled by BD was wrong. Okay, we had assumed it, but there is no issue with that. Okay, we can assume because initially we won't know which direction this will be acting, so anything is fine. So now it is telling you that in fact dx should have been in this way. So that means the BD is actually pushing the pulley in that direction with 5000 Newton of force. So that's one. And then if you write the equations in d in the y direction, summation of say summation of fy, if you take to 0, you will find out dy. Okay, so find out dy. So dy will come to be some 6962 Newton. Okay, so that you should figure out. Yeah, it's very simple. Mg should be equal to that because no other. So this is there. T prime plus dy plus mg is equal to 0. So T prime is known, mg is known. So dy you can figure out. So this is 5000 Newton plus this is 200 kg times 9.8 if you put. So you get this. Okay. Great. So then what? So dx dy are known, and then what we can do is. We can now come here and write the equation of moment about this, because so that if you write a moment about this, which again is very important to observe, that you should write you should take the point about which you take the moment, it should contain many unknowns so that you can get rid of as many as possible. See here, if you take a moment about this point, these two are gone in the equation, they won't come. Cx will be gone, dx will be gone. So only thing which you will require is dy, and cy is the unknown, and you will be able to figure this out. So that is what we have to do. So take moment, say, and then say in the FBD 1, in the FBD 1, take moment about B, summation of all the moment to 0. Okay. So if you do that, in fact only thing which will be required is this distance. How much is this distance? It is, I think, 4 meters, isn't it? And then this distance is 4 plus 2.5, 6.5. So that means 4 times your, what was that name given? Cy. Okay, 4 times Cy plus 6.5 times dy is equal to 0. So from here you can get Cy to be equal to how much? It's coming to be say 11,313 Newton. Okay. So okay. So I think there are some sign issues. When you calculate this, the dy which you would have got also would be in the negative direction. Okay, so there is in the way I have taken, you would be getting actually a negative sign here when you solve this. So this is 1. So this is 1. So dx and dy. So basically both the directions which we had taken were wrong in a way. I mean, there is nothing wrong. Our assumption was wrong that dx is in this direction and dy is in this. Doesn't matter. Okay. So then, if you consider that, then Cy will come to be this. Okay. Okay. Then what? Then what? Let's say we have only one unknown now remaining, right? That is Cx, which we need to figure this out, because now here we don't have any point about which if you write a moment you will get it. So what we will do is we will come over here to this and we will write a moment equation about this. So let's say we will go to free body. So here I'll put this. So I'll go to free body diagram. Say that was what, 2. Free body diagram 2, and I'll write a moment about the point A. I'll sum them all to 0. Now what they will be, say about this, now Cy times this distance, whatever is that, 4 meters. One more force, here there was a mistake, isn't it? So this force I never showed, so that should have been here at that would be how much? 14 Newton, right? So 7 newtons per meter for 2 meters, so 14 Newton, but at what distance? At the center point, because it's uniformly distributed. So from here this distance is 1 meter, so that is from here it should be at 1.3 meters, right? So at 1.3 meters, 14 Newton of force also is acting. That's it. So then when you write the equation of moment equation about this, you get so this 14 Newton times 1.3. So 14 times 1.3 plus this the same direction, 4 meter into Cy was how much? Cy is this much. So 11,313 times 4. Then this is in the opposite direction, minus Cx times that distance is this distance, isn't it? This is 2.5 meters. So minus Cx times 2.5 meters. This goes to 0, and if you solve this, you should get what is that value? Cx should one more thing I think I have missed out. This T is 5,000 newtons. Okay, plus, so here I should write also plus T times, and that distance is how much? This was 2.5 plus 0.6, so that is 3.1. Good. So T into 3.1. So that also should have been there. Okay, so if you do that, Cx you will get as say 24,300 newtons. That's it. So these are the two things you were supposed to find out, Cx and Cy. So in fact you can write that at C the vector is, so 24,300 I plus 11,313 J. Okay. So this is the answer to that question, saying that, okay, now see how you should write even the final answer, that is that C is that force which the body AC is acting on BD, because that is how we have mentioned Cx and Cy to be those forces, right? Cx is in this direction, Cy in this direction. Or you can say that BD is acting with that force C on this. Okay. In fact, here when I am writing Cx, Cy, so they are the magnitudes, not the vectors. Okay. So this is the force, because the way I have mentioned here. So this force is, force of AC on BD, because here I am using the positive and the positive numbers. Okay. Good. So that's how that problem was supposed to be solved. Good. We will see another problem in the next segment.